On July 1st, 2026, a telescope in the Chilean Andes captured the first image of its decade-long mission. Not a test image, not a calibration frame. The actual first image of the legacy survey of space and time, the most ambitious astronomical survey ever attempted by any civilization on Earth. And the image it captured was a 1.7 gigapixel portrait of stars in the constellation Lupus, a star-forming region in the southern sky that had never been photographed with this level of detail, this sensitivity, and this sheer number of pixels at one time. That image marked the beginning of something that astronomers have been waiting for since the turn of the century. The greatest cosmic movie ever made has started filming, and the camera doing the filming is unlike anything that has ever been built. And U.S. National Science Foundation Director Brian Stone said it with perfect simplicity on the day the survey began. He said, "Today, we begin filming the greatest cosmic movie ever made." That is not a metaphor. Rubin will photograph the entire southern sky every 3 nights for 10 years, stacking those images on top of each other to create a time-lapse record of the universe that will show everything that changes, moves, brightens, fades, explodes, or appears for the very first time. No previous observatory has attempted anything at this scale, and no previous observatory has had the camera to attempt it. The story of the images that have already come from Rubin begins not on July 1st, but almost exactly a year earlier. On June 23rd, 2025, the Vera C. Rubin Observatory held its first look event in Washington, D.C., unveiling the first images captured with the LSST camera to the public. Officials unveiled large, ultra-high-definition images at a ceremony watched by astronomers around the world, including at watch parties hosted by universities and planetariums across multiple continents. And what they showed stopped every person in every room that was watching. The centerpiece of the first look release was a composite image combining 678 separate exposures taken in slightly more than 7 hours of observing time. The target was the region of sky containing both the Trifid Nebula and the Lagoon Nebula, 2 spectacular star-forming regions several thousand light-years from Earth that have been photographed hundreds of times before by telescopes of all sizes. But what Rubin showed was different in kind, not just degree. The Trifid and Lagoon nebulae appeared in vivid pinks and reds against orange-red backdrops, glowing in a composite that revealed previously faint or invisible features, the delicate gas filaments, the dense dark lanes, the subtle variations in ionization across the nebulae that had been beyond the reach of every previous ground-based instrument. The entire image was 50 times larger than what was displayed on screen during the first look event. Rubin Observatory Director Zeljko Ivazic told reporters that the entire image was 50 times larger than what they were seeing on screen. What they saw was already breathtaking. What was not being shown was 50 times more. A second first look image showed the Virgo cluster, the nearest major galaxy cluster to the Milky Way, containing approximately 2,000 individual galaxies spread across a region of sky larger than what most telescopes can capture in a single pointing. Rubin showed all of it. Thousands of galaxies, from the massive elliptical giants that dominate the cluster's core to the faint dwarf. Galaxies at its edges that had previously required dedicated deep observations to detect at all, captured simultaneously in a single sweeping image that conveyed the true three-dimensional structure of the cluster in a way that no previous image had managed. Scientists studying galaxy evolution, dark matter distribution, and the large-scale structure of the cosmos immediately recognized the Virgo cluster image as a demonstration of exactly the kind of science Rubin was built to do. What made both first look images scientifically stunning was not just the visual detail, it was the depth. Combining 678 individual exposures of the same patch of sky stacks the light from the same sources over and over, effectively giving the telescope a longer total exposure time than any single observation could provide, while simultaneously averaging out the noise that accumulates in any individual frame. This stacking technique has been used by astronomers for decades, but Rubin's speed means it can stack far more images in a much shorter time than any previous instrument. The 678 exposure composite took slightly more than 7 hours of actual telescope time. With Rubin's cadence, that kind of depth is achievable in every patch of sky across the entire survey, repeated again and again across 10 years. By the end of the decade-long survey, the deepest co-added images of any region of the sky will reveal objects hundreds of times fainter than any individual Rubin exposure can detect, probing the universe at depths that were previously accessible only to the Hubble Space Telescope's deepest targeted observations. The period between the June 2025 first look and the July 2026 official survey launch was not idle. On the night of February 24, 2026, Rubin sent out 800,000 astronomical alerts that directed astronomers' attention to new asteroids, supernovae, and other transient phenomena. That single night of commissioning observations produced more astronomical alerts than the entire annual output of the Zwicky Transient Facility, the previous gold standard for wide-field time-domain astronomy, and each alert represented a real event, a real change detected in the real sky, delivered to astronomers around the world within 2 minutes of the observation being taken. A supernova detected in a galaxy millions of light years away at 2 a.m. Chilean time could trigger a spectroscopic follow-up observation from a telescope in Hawaii or the Canary Islands before sunrise in South America. Through images taken to help optimize the system before the survey officially began, the observatory already detected 11,000 new asteroids and logged dozens of other new objects in our solar system. These pre-survey discoveries were essentially accidental. Rubin was not yet in full survey mode. It was still calibrating, optimizing, and validating its systems. And in the process, almost as a side effect of pointing the camera at the sky during tests, it found 11,000 asteroids that had never been cataloged before, including dozens of near-Earth objects and hundreds of trans-Neptunian objects in the distant outer solar system beyond Neptune's orbit. Full survey operations will produce asteroid discoveries at a rate that will transform the catalog of known solar system objects within a few years. The decision to officially launch the LSST on June 30th, 2026, after a period of careful validation rather than earlier as originally planned, reflected the team's commitment to ensuring every component of the system was performing exactly as required before committing to the 10-year survey cadence. Rubin Observatory Director Zeljko Ivezic said the decision to officially begin the LSST was made after a period of system optimization and a careful operational review of technical readiness, data system performance, and scientific validation. That caution paid off. The first night of official LSST operations on July 1st, 2026 produced what the team described as a flawless observing run, with the 3.2 gigapixel camera operating at full sensitivity across all 189 of its detector sensors, and the data pipeline delivering fully processed images and alerts to the global astronomical community within the target 2-minute window. The 1.7 gigapixel first LSST image, captured in the constellation Lupus on July 1st, 2026, represented something different from the June 2025 first look images. Those images were carefully chosen showpiece targets, selected to be visually spectacular for the public announcement. The Lupus image was the routine. It was what Rubin looks like when it is simply doing its job on a normal night, pointing at the next region of sky in its systematic survey cadence, collecting light, processing data, and moving on. Lupus, a constellation of the southern hemisphere containing several active star-forming regions at distances between 400 and 600 light-years from Earth, is one of the nearest sites of ongoing stellar birth in the Milky Way. Young stars in Lupus are still embedded in the gas and dust clouds from which they are condensing, and the infrared and optical emissions from those clouds, captured in exquisite detail by the 8.4-meter Simon-Yankee Survey Telescope, revealed structures in the star-forming environment that previous surveys had not resolved at this scale and depth. The scientific architecture of the legacy survey of space and time is built around 4 primary science goals that were established when the survey was first proposed more than 2 decades ago, and that have been refined and validated through 2 decades of observational preparation. The first is dark energy, by measuring the shapes of billions of galaxies across enormous volumes of space, and looking for the statistical distortion in those shapes caused by the large-scale structure of the universe. Rubin will produce the most precise independent measurement of dark energy's properties ever attempted. The standard model of cosmology treats dark energy as a cosmological constant, but mounting evidence from multiple observatories suggests it may evolve over time. Rubin's measurements will either confirm the standard model or provide the most compelling evidence yet that something new is happening in the physics of the universe at its largest scales. The second goal is dark matter. By mapping how galaxies cluster and how those clusters evolve over billions of years of cosmic history, Rubin will probe the distribution of dark matter, the invisible substance that makes up 85% of all matter in the universe, and whose gravitational influence holds galaxies and galaxy clusters together with a precision that no previous survey has achieved. The third is the exploration of the changing sky, cataloging every type of transient astronomical event, from supernovae to active galactic nuclei, to gravitational lens events, to variable stars, to gamma-ray burst afterglows, building the largest statistical sample of astronomical transients ever assembled. The fourth is the solar system inventory, cataloging millions of asteroids, comets, and other small bodies, in orbits ranging from near Earth to the deep outer solar system, including the population of potentially hazardous near-Earth objects that planetary defense requires to be tracked. Before the official survey began, during the optimization phase that ran from late 2025 through June 2026, Rubin produced several images shared publicly as demonstrations of what was coming. Among those was an image nicknamed the Cosmic Treasure Chest, a deep field observation packed with galaxies at various distances from nearby spirals whose individual star-forming regions could be resolved into distinct clumps of blue light, to distant red smears of elliptical galaxies billions of light years away, to faint background galaxies so distant that the light arriving in the image left them when the universe was a fraction of its current age. The Cosmic Treasure Chest image covered a region of sky that would take Hubble thousands of individual pointings to match in coverage, yet was captured by Rubin in a single routine test observation. That trade-off, broad coverage rather than extreme depth, is precisely what makes Rubin's science uniquely valuable for statistical studies of galaxy populations, dark matter distributions, and the large-scale structure of the universe. The multi-wavelength strategy of the LSST is one of its key design features. So the LSST camera is equipped with 6 filters designated U, G, R, I, Z, and Y, covering wavelengths from near ultraviolet through the near infrared. As the telescope sweeps through its survey cadence each night, it cycles through these filters, building a color portrait of every object it photographs across multiple wavelengths. Different types of objects have characteristic colors in these filter combinations that allow automated classification algorithms to distinguish supernovae from variable stars, from quasars, from asteroids, from gravitational lens events, a type Ia supernova, which is the most important type for cosmological distance measurements and dark energy studies, because it has a predictable intrinsic brightness that allows it to serve as a standard candle across cosmic distances, has a characteristic color evolution over days and weeks that stands out distinctively in Rubin's multi-filter light curves. Rubin is expected to discover more type Ia supernovae in its first year of operations than have been discovered in the entire history of supernova astronomy combined. The AI and machine learning infrastructure that processes Rubin's data is as revolutionary as the telescope itself. The entire process runs autonomously, without human review, at a speed and scale that makes human oversight of individual alerts impossible given the volumes involved. The alert broker systems operated by institutions, including the alert management, photometry, and evaluation of light curves, LASER, and the automatic learning for the rapid classification of events, use machine learning. Classifiers trained on labeled data sets of known object types to sort, prioritize, and route the millions of daily alerts to the researchers and follow-up telescope systems most likely to find them scientifically useful. What this infrastructure means in practice is that Rubin is not just a telescope. It is a discovery engine with a nervous system. The moment a new supernova appears in a galaxy 500 million light-years away, an automated alert is generated, classified as a likely supernova by the machine learning system, and delivered to supernova researchers around the world within minutes. Those researchers can then trigger follow-up spectroscopic observations through automated target of opportunity programs at other telescopes, potentially capturing the earliest phase of the supernova's light curve that contains information about the explosion mechanism and the properties of the progenitor star that cannot be recovered once the early phase has passed. The speed of this pipeline, from photons to alerts to follow-up observations within hours, represents a transformation in how domain astronomy is conducted that has no precedent in the history of the field. The survey's impact on planetary defense is already being felt even before the full survey cadence has completed its first month. Rubin's ability to detect objects as faint as 24.5 apparent magnitude, roughly 40 times fainter than what the Catalina Sky Survey can detect, combined with its all-sky cadence of 3 nights, means it will find near-Earth objects that current surveys are missing. NASA's Center for Near-Earth Object Studies has estimated that Rubin will more than double the total number of known near-Earth objects within 5 years of full operations, and will dramatically extend the warning time available before potential impacts from objects in the size range most likely to cause regional to continental damage. The LSST is expected to transform our understanding of the NEO population. For planetary defense, which depends critically on knowing where the dangerous objects are before they become emergencies, that transformation cannot come fast enough. The next decade of Rubin operations will produce a dataset so large that the astronomical community is already building the computational and human infrastructure needed to analyze it. The total data volume of the LSST over 10 years is estimated at 60 petabytes of raw images and 15 petabytes of catalog data, the largest astronomical dataset ever assembled by any single instrument. Analyzing that data will require the combined resources of hundreds of institutions, thousands of researchers, and computational facilities specifically built and funded for the purpose. The Rubin Science Platform, the software infrastructure that will allow researchers around the world to access and analyze the survey data without downloading the entire archive locally, is a parallel engineering achievement of comparable ambition to the telescope itself. The woman the observatory is named after would recognize the ambition, if not the technology. Dr. Vera Rubin spent her career measuring the rotation of galaxies at observatories with instruments that would seem primitive by the standards of the 8.4-meter Simone Survey Telescope and its 3.2 gigapixel camera. She did her work by hand, on punch cards, at telescopes where she was sometimes the first woman allowed to observe at that facility. She was nominated for the Nobel Prize in Physics multiple times and died in December 2016 without receiving it. The Nobel Committee has never awarded the prize posthumously, a policy that has excluded some of the most consequential scientists in modern history from the recognition their work deserved. The observatory bearing her name is now conducting the most precise measurement of dark matter's distribution in the universe ever attempted. Every image it captures, from the Trifid and Lagoon nebulae of June 2025 to the Lupus star-forming region of July 2026 to the billions of galaxies it will photograph over the next decade, is a direct continuation of the work she began in the 1970s when she first noticed that galaxies were rotating in ways that could not be explained without invisible mass. The Nancy Grace Roman Space Telescope, launching August 30th, 2026, will add a complementary capability to the Rubin data stream from the moment it begins operations. Roman's 2.4-meter space-based mirror, operating above the atmosphere, will provide sharper images of the same sky patches that Rubin surveys from the ground. The two observatories were designed in deliberate scientific partnership. Rubin provides wide-area statistical power. Roman provides precise, distortion-free measurements of individual galaxy shapes. Together, they are expected to produce dark energy measurements precise enough to definitively distinguish between a cosmological constant and a dynamical dark energy model that evolves over cosmic time. That distinction is one of the most important open questions in all of fundamental physics. The main actors in Rubin's LSST production will be pulsating stars, supernova explosions, fossil records of galaxies, and entirely new phenomena that nobody has yet predicted. Every major sky survey in the history of astronomy has discovered something no theory anticipated. The Sloan Digital Sky Survey revealed the full three-dimensional structure of the cosmic web. The Dark Energy Survey found tensions in the standard model that remain unresolved. The Zwicky Transient Facility discovered the first confirmed interstellar comet. Rubin will survey more sky, more deeply, more frequently, than all of those surveys combined. Whatever it finds that nobody predicted, whatever cosmic phenomenon has been hiding in the night sky waiting for an instrument sensitive enough to detect it, will be among the most significant astronomical discoveries of this generation. The first image was captured on July 1st, 2026. The last image of the legacy survey of space and time will be captured approximately in 2036. In between, every night, this telescope will watch the universe change, and some of what it sees, nobody alive today can predict. The main actors in Rubin's LSST production will be a cast of pulsating stars, supernova explosions, and fossil records of galaxies. This will not only provide clues as to the nature of dark matter and dark energy, but could also reveal hitherto undiscovered cosmic phenomena. Those last 5 words are the ones that keep astronomers most excited. Every major sky survey in the history of astronomy has discovered something that no theory predicted. The Sloan Digital Sky Survey revealed the cosmic web. The Dark Energy Survey found tensions in the standard model. The Zwicky Transient Facility found interstellar comets and unusual solar system objects. Rubin will survey more sky, more deeply, more frequently than all of those surveys combined. Whatever it finds that nobody predicted, whatever cosmic phenomenon has been hiding in the night sky, waiting for an instrument sensitive enough and fast enough to detect it, will be among the most significant astronomical discoveries of this generation. The first image was captured on July 1st, 2026. The last image of the legacy survey of space and time will be captured approximately in 2036. In between, every night, this telescope will watch the universe change, and some of what it sees, nobody alive today can predict.